So this is the differentiation property xt Fourier series t naught ak x dash t. I'm considering only the first derivative jk omega naught into ak. So this is if we denote it by bk. Okay. Now if you are considering a signal xt, what about this signal if its integral? Will it be a periodic signal? If you consider any signal xt, consider this integral, will it be a periodic signal?
Yes, sir.
It is always a periodic signal. Integral of a periodic signal is always periodic signal. Is it? And remember when I say integral means I am not talking about the area, I am considering this integral minus infinity to t. Okay. Otherwise area is always a constant value. This is a function of t. Will it be always periodic? For example, this signal, if you consider xt, let's say this is 0 t1, this is t naught. What is the integral of this? Will it be a periodic signal?
Sir.
Yes.
Sir.
Yes. And this is 0 and this is 1. Is it a periodic signal?
No, sir.
No. Why not?
Sir, because the value of integral will increasing.
Value of the integral
Will keep on increasing as
will keep on increasing. So now can you tell me what is the condition for this to be periodic? It can be periodic also, isn't it? Integral
If
of
the
a,
average of the
if the
if average of the original signal is 0.
if average of the original signal is 0, then the result the integral will also be a periodic signal, isn't it? So that is the
Yes, sir.
condition. The integral of a periodic signal is periodic only if xt, the average value of xt is 0. Average value of xt is 0. Then only this is periodic. And then only it makes sense to find the Fourier series representation of integral of a signal. Okay. And you can easily verify this also. Given a periodic signal, you can suppose this is the periodic signal xt, and you can always write it as a periodic signal having 0 average value. I am writing it as x naught t. A periodic signal having 0 average value plus a constant. Is it? Given any periodic signal xt, can we write it as a periodic signal with 0 average value plus a constant? For example, this one. This can be written as, what is the corresponding signal with 0 average value? You have to shift it down by how much? Not half, it is dependent, it is okay, let's say it is 2t1 by t naught, isn't it? The average value of this signal is 2t1 by t naught. So if you shift it down by 2t1 by t naught, you will get a signal having 0 average value. So we can say that if you are given a periodic signal, we can always write it, express it as a sum of a signal having 0 average value plus a constant plus this shift. Okay. Now what will happen if you integrate this? Is it this? Oh, sorry, it is integrate with respect to, sorry, it is t. You have to integrate x tau, isn't it? Because, yeah. So what will be the integral? What about a periodic 0 average value? If you integrate a signal having 0 average value, then will it be a periodic signal, resulting signal?
Yes, sir.
Yes, you can easily verify this also. Like, let me draw it. So let's say this is a signal having 0 average value. If we start from here, after one period, what will be this integral? What is integral over one period? It is 0, right? So if we increase the value of t, that will that will not keep on increasing. But if the average value of the signal is non-zero, that means this c is not 0. Then what will happen to this term? What will be the shape of that? There is a constant term. Any periodic signal can be expressed as a signal having 0 average value and a constant term. Now, if we integrate that signal, what is this term? If the constant is non-zero, what will be the shape? Can we say that this part is a periodic signal? Plus, what about this? If it is
linearly increasing.
it is linearly increasing function, right? So the sum of these two cannot be a periodic signal because this term is linearly increasing. That's why the condition is that the average value of the signal must be 0. Then only we will get the integral of a periodic signal will be periodic. Is it clear? Okay, now let us discuss the integration property. So xt Fourier series T naught ak. If the average value of the signal is 0, then we can say that this is also a periodic signal. Is it? If the average value of the signal is 0, then what about ak? What is a0? If the average value of which signal? Average value of xt is 0, then its integral is also a periodic signal. If the average value of xt is 0, then what is a0?
Zero.
A0 is 0. I am assuming that a0 is 0, that is xt is a periodic signal with average value 0. So its integral is a periodic signal with the same period. And it's bk. Can you tell me what is the relation between bk and ak? We have discussed the differentiation property. What is differentiation property? If you have a function, let's say the Fourier series coefficient of a signal is ak, then its derivative, the Fourier series coefficient of its derivative is j k omega naught into ak. That is the differentiation property. Now, if you apply differentiation property to this signal, this Fourier series pair, what will happen? What is the derivative of this? xt. That is a Fourier periodic signal T naught. And this one, what is it? Is it j k omega naught into bk? Bk. So does it imply that this is equal to ak?
Yes, sir.
And bk is equal to ak by j k omega naught. That is the integration property. But there is a problem here. Can you tell me what is the problem?
K equal to 0.
The problem is that this expression is this is valid because the integral of a periodic signal is periodic only if a0 is 0. Okay. And here, this one, is it? So if you put b0, can you find b0 here? Is it possible to find b0? Because it is a0 is 0, k is 0, it is 0 by 0 form, isn't it? We cannot find b0. So the integration property says that if xt Fourier series coefficient ak, this one, so what we can write is, we can make b0 0, ak bk, so bk is equal to ak by j k omega naught. Okay, let me write. This is bk is equal to 0 when k is equal to 0 and ak by j k omega naught when k. Okay, this is what we can get. We cannot find the average value of this signal. We cannot find the value of the Fourier series coefficient at k is equal to 0. So what we can do is we can make it 0. That means we are getting the Fourier series coefficient of which signal if we apply the integration property? And what is the reason for this 0 when k is equal to 0? Okay, it will be clear when we discuss this example. So let us consider this example itself. Zero t1 minus t1, 0, this is t naught. It is a periodic signal and its derivative is this one, isn't it? 0, this is t naught. This is minus t1. It is a periodic signal and this is t1. Its strength is 1 and this is minus 1. This is a worked out example in Oppenheim. You are given you have to find the Fourier series coefficients of a periodic signal, a rectangular pulse train starting from here. How to find when you integrate, will you get the signal? What is the integral of this? Is it this one? This is the derivative, isn't it? This impulse train, this is the derivative of this rectangular pulse train. My question is this the integral of this? Or can we apply, can we use the integration property to find the Fourier series coefficient of this?
Yes, sir.
What are the Fourier series coefficients of this signal? And for that, you have to, I hope you remember the standard result. Summation k from, let's say m from minus infinity to infinity delta t minus m t naught. What are the Fourier series coefficients? Fourier series with respect to period t naught. That is the Fourier series coefficient of an impulse train. If it is a periodic signal with period t naught, these are the Fourier series coefficients. Now, can you find the Fourier series coefficient of this signal using this property and some other properties of Fourier series representation? First of all, what is the expression for this signal? What is the expression for this signal? Let's say this is the signal. Okay, this is the signal xt and this is x dash t. What is this one expression for this signal? In terms of this impulse train, it is sum of two impulse trains, isn't it? If you consider the impulses having positive this strength, this one, is it an impulse train? What is the period of that signal? If you consider this having the positive peaks, positive that strength, is it a periodic signal?
Yes, sir, of period t naught.
Of period t naught. What is the expression for that signal? This one, this positive part. Is it delta? What is the expression? Is it a impulse train shifted left by t1?
Yes.
Yes.
This is the impulse train. This impulse train means there are impulses at 0, t naught, 2 t naught like that. And here this one, it is shifted left by t1. So what is the expression? Is it delta t minus or plus? T plus t1. Is it this? This is the expression for the impulse train, that is 0 impulses at 0 t naught to t naught. And here this one is shifted left by t1, that is replacing in this. What is the operation replace t with? What is the operation for shifting left by t1? Is it replace t with t plus t1?
Yes, sir.
That is shift left. Then we get this expression. Minus what? Now what about the negative part?
Delta t minus t1 minus n naught t naught.
Minus infinity to infinity delta t minus t1 minus m t naught. Is it?
Yes, sir.
Now tell me, what are the Fourier series coefficients of this? You have to use which property? This is the standard result. We know the Fourier series coefficients of impulse train. What is the Fourier series? What are the Fourier series coefficient of shifted that impulse train? This is the property, time shifting property. If xt Fourier series coefficients are ak, then what about this t minus t naught? It is ak into e to the power minus jk omega naught t. Oh, sorry, naught t is not there. E to the power minus jk omega naught. Omega naught t naught. Okay. Multiplication with a complex exponential if you shift in the time domain. So what are the Fourier series coefficient of this? If you are assuming that the Fourier series coefficients of okay, these are ak. You are trying to find the Fourier series coefficient of this impulse train. Let's say it is ak. So what is ak? Is it 1 upon t naught into what? E to the power minus, sorry, it is plus jk omega naught. And what is omega naught t1? Is it this? Fourier series coefficient of this first part.
Yes, sir.
And what about the second part? There is a minus sign because of this strength is minus. What is the Fourier? What are the Fourier series coefficients of this? Is it 1 upon t naught?
E to the power minus jk omega naught.
Minus jk omega naught t1. Is it? We can simplify this. This is equal to 2j sine k omega naught t1 by t naught. Is it?
Yes, sir.
Yes. Now my question is, we have found the Fourier series coefficients of this one. Can we find the Fourier series coefficient of the coefficients of this rectangular pulse train using the integration, this result and the integration property?
Yes, sir.
How? What is the integration property? Let's say this one is the, okay, for that I am taking this as, okay, there is a confusion. Let's say this is the signal xt and this is the integral of the, we want to find the signal Fourier series coefficient of x1t and this is the signal xt. We are starting from here, found the Fourier series coefficients. Now using the Fourier, the integration property, we have to find the Fourier series coefficients of the signal x1t, and let me denote the Fourier series coefficients by bk. Now what is the integration property says? What does it say?
So bk equals
bk is equal to
ak upon jk omega, ak upon jk omega naught. That will be
jk omega naught, isn't it? So if you apply it here, it is 2 sine what? K omega naught t1 by t naught. That is the integration property. But remember, this is valid only for which values of k? This is valid only
or
for
k not equal to
when
0.
k not equal to 0, because this is a signal having average value 0. So the A0 is 0. And if you put k is equal to 0, that is not a valid expression, isn't it? So this is
So do
for
we always have, so do we always have to put it B0 is equal to 0, or can we like find the limits?
no. I am coming to that point. I am not saying that definitely this one is B0 is not equal to 0. Is this 0 here?
No, sir.
No, it is not 0. But we can. What I am saying is we cannot determine that average value from this integral of this. It is not possible. Particularly when you apply the integration property, what you get is this one. Okay, something is missing here. Is it T naught? There is an omega naught, isn't it? When you divide with j, k omega naught, it is T naught omega naught 2 sine k
The
omega.
K also. K also.
Yeah, k omega naught T naught. Okay, and if you remember, this is the standard result we have proved earlier. And this is for k not equal to 0. Okay. Now the integration property says that, okay, B0 is 0. That is the best thing we can do. We cannot find the average value of this signal from the integral of this. Okay. Now if you put average value 0, that does it corresponds to this signal or some other signal?
A signal with the DC shift x1 t having a
Signal with the DC shift. B0 0 means a signal having average value 0. Now we have to find the Fourier series coefficient of this signal. So what we have to do? We have to find the average value of this signal. Is it? What is the average value of this signal? If you are given the signal, we can directly find the average value. What is the average value?
2T1 by T naught.
2T1 by T naught. Okay. So using the integration property, we can find the values of the Fourier series coefficients for all the values other than k equals 0. And for k equals 0, you have to find the average value of the signal, and that is the B0, isn't it? Is it? Is it
Yes,
that? Yes. And this is same as the standard result. And in this particular case, can we write the expression as this? 2 sine k omega naught T1 by k omega naught T1. What is the value of this as a limiting case when k tends to 0? What is this?
2.
What 2? Sorry,
Value
there
will
is
be 2
something
limit.
missing. It is k naught omega naught T naught actually. It is not T1. What is the value when this is in the limiting case as k tends to 0?
2T1 by T naught.
It is 2T1. It is 2T1 by T naught. It is the same as this. And remember, it is not always true. In this case, we can write the expression as this is for all the values of k. Okay. Otherwise, most of the cases you have to write the expression for this separately. Here, this expression is valid for all values of k. Okay. So that is how we find the this Fourier series representation of a signal using the integration property. The average value for B0 of that signal, if you find the Fourier series coefficient of any signal using the integration property, you cannot find the average value of the signal from its derivative. That one you have to find from this and directly substitute it. For all other values, you can use the integration property. Okay. Okay, let us consider one more example. Let's say,
Sir, can you repeat the B naught now? Just now you said about integration.
B01.
Yes, sir.
Okay, so this is the integration property. Bk is equal to ak by jk omega naught, isn't it? That is the integration property. And we
Yes,
know
sir.
that this integration property we can apply only when the average value of the signal is 0. That is A0 is always 0. And you cannot, what I am saying is you cannot find B0 from this expression.
Yes, sir.
So what we can do is make it 0. then you will get the Fourier series coefficient of a periodic signal, corresponding periodic signal having DC value 0. Then depending on the signal, you have to adjust the DC value to get the Fourier series coefficient as 0, B0. That is what I am saying. Is it clear?
Sir, means finally B0 is 0 or not? Sir?
No, B0 is not 0. That is what I am saying. In this case, B0 is not 0. You have to find it separately. You cannot find it using the integration property. B0 is not 0. B0 is in this case is 2t1 by t0. Okay, let us consider.
Means we
yes.
are doing the limit function now, sir. Yeah.
Not
Limit k
limit,
tends to-
not limit function. What I am saying is this expression is valid for that also, but actually the value is 2t1 by t0. So you can, in this case, you can write it as a same function for all the values of k. That is a valid function. Okay. Okay, that will be clear from the next example. This